Test generation is one of the very important steps in the testing process, because this is where the test patterns are generated for given a circuit description and a list of faults. So, this test pattern generator, so they are supposed to generate the test pattern that should be applied to the circuit to check whether the circuit is okay or not. So, corresponding to a test pattern, so there will be a good response that is coming from a good circuit, and in the presence of some faults, that response will be different. So, based on that we can find out, we can detect those faults that may be present in the circuit. So, this test generation process, so we will go like this. So, we will first look into the introduction, general introduction to the problem, then we will discuss about random test generation. So, random test generation means we randomly apply some test patterns and see whether some faults are getting covered or not. And it is interesting to note that a good number of faults are detected by some random patterns, and it is many a times it is up to 70 to 75% faults of a circuit that are detected by random patterns. So, the remaining faults, so there we need to be cautious, and actually this test generation algorithm, so this needs to be applied for the remaining 25%, about 25% of faults. Then we will go into the theoretical foundations, then deterministic combinatorial ATPGs, then how to detect some untestable fault, that is some fault that are untestable. So, if we can remove those faults from our consideration, then naturally this test generation process will be faster, because it will not target on those untestable faults. Then certain ATPGs are based on simulation based on simulation. So, basically algorithms that use genetic algorithm or some such evolutionary techniques. Then there are some delay and bridging faults. So, they need some special type of ATPGs. So, they will be covered at that time. Some other topics, and then we will go into the concluding remarks. Test generation is the bread and butter in VLSI testing. So, this is a quite common statement, because this is what this test generation these test engineers, so they are doing. So, they are trying to ensure more and more coverage of the faults in the circuit. So, if we are trying to do that, then definitely we should have a very good test pattern set to be applied to the circuit. Efficient and powerful ATPG can alleviate the high costs of DFT, because if the DFT means we need to have some extra controllable and observable points added into the circuit, whatever be the technique, ad hoc technique or structured technique, whatever it is. But if the ATPG itself is very good, and if the ATPG algorithm can itself give us a coverage of high number of faults, then definitely we may not be requiring so many points, so many controllable and observable points in the circuit. So, as a result the cost of DFT can go down. So, the goal is to generate a small set of effective test vectors at a low computational cost. So, this is also another important issue, because you see whenever we are generating a set of test patterns or a particular or a single test pattern, we need to know what are the faults that this pattern can detect. Maybe previously we have generated 100 patterns, and those 100 patterns have covered some 10,000 faults present in the circuit. Now, the 101st pattern that we are going to generate, it must be able to uncover some faults which are not yet detected by previously generated 100 patterns, otherwise this is of no use. So, we are definitely interested to have a good coverage, and we want effective vectors, and this effective vector generation process should not be computationally very expensive, because then the applicability of that particular algorithm may be in question. ATPG is a challenging task, because the problem is exponential in nature. So, if we are trying to generate the exact minimum test set for a particular circuit for a particular set of faults, then this problem is exponential. So, we have to take help of heuristics, and the heuristics must be running in reasonable time and giving us a good amount of fault coverage. Circuit sizes continue to increase by Moore's law. So, it is doubling after a regular interval of time. So, it aggravates the complexity problem further. So, this more number of devices put into the circuit means we have to have more number of faults, and then naturally we need more number of patterns to test them. Clock frequencies are increasing. So, we need to test both structural and delay defects. So, if the clock frequency increasing means the gate delays should be such that this combinatorial gate delay should be such that the evaluation of the input occurs within the clock duration. So, if the clock speed is high, then there is a high chance that some of the gates will have some problem in them and the delays may not be within the clock duration. So, as a result it will have more number of delay defects. So, delay defect handling becomes an important issue. Conceptually, an ATPG can be viewed like this. So, we have got a defect free circuit and a defective circuit. The inputs are applied to both the defect free and defective circuits. So, if suppose X is the defect, so X is the defect, it manifests as some fault in the circuit. So, under that fault or defect, whatever you call it, that defect X, the defective circuit output and this defect free circuit output, they should be different. As a result, if we XOR them, so we will get a logic 1 at the output. So, the challenge is that we are given this defect free circuit and this defective circuit, and knowing that we have got an XOR gate at the output of these two, where the outputs of these two circuits have been XORed. So, we have to design an input vector such that this XOR gate output is at logic 1. So, XOR naturally, if these two outputs differ, then it will be in logic 1. So, we have to derive this particular input set. So, as we have already seen that physical defects are not handled directly, rather we have some fault models, and with respect to that fault model we need to generate the test pattern set. So, fault models that we will be considering in this part of our lecture are staccato fault, bridging fault, transition fault and path delay fault. So, these are the types of faults that we will be covering in this part of the lecture. Let us start with a simple example. Okay. So, consider a fault which is say D stuck at 1. We want to, so this is the circuit having 3 inputs A, B, C and 1 output E, and we want to detect this particular fault D stuck at 1. Now, to check to test this fault, two things are necessary. Since this line is stuck at 1, so first of all we need to force this line to 0. Any test pattern that we will apply here should try to force this line to 0. And how can this be done? Since this is an OR gate, putting A and B both the inputs to 0, I can get a 0 at the point D. So, we need to excite the fault which is in terms of opposite of the fault that we want to detect. So, we want to detect stuck at 1. So, we have to force a 0 here. For that, this A and B must be equal to 0. Now, the line D is not directly observable. So, observable is the line E. So, somehow that effect has to be propagated through this AND gate, and we must get the response at E. And for that purpose, this other input of the AND gate, it must hold a non-controlling value. So, this C input must be at a 1. So, you see that we have to apply A equal to 0, B equal to 0 and C equal to 1. So, if we do that, then in a fault free circuit, this line D is at 0, C is at 1. So, E is at 0. In a faulty circuit, this line D will be at 1 because this is stuck at 1, and C is also 1. So, E will be at 1. So, fault free response is 0, faulty response is 1. So, we say that this particular pattern 0 0 1, it can detect this particular fault D stuck at 1. A typical ATPG system will work like this. Given a circuit and a fault model, what it will do? It will repeat the following steps. What? Generate a test for each undetected fault. So, initially all the faults in the circuit are undetected. So, it can try to generate a test pattern for that. So, if it successfully generates one test pattern, so certain faults in that set gets detected. So, those faults we need not consider anymore. So, in our successive attempt, we should be trying some other faults which are not yet detected. So, that is what is coded written here. So, generate a test for each undetected fault and drop all other faults detected by the test using a fault simulator. So, there are a number of faults. So, we just pick up one of those faults and target it for test generation. So, the corresponding test pattern, so it will detect not only this particular fault, but maybe some more faults as well. So, when it does it, so when it does that, then all those faults can be dropped from the set, because those faults are also detected by that pattern. So, for example, in this case you see that if this output E changes from 0 to 1. So, if you are trying to check E stuck at 0, then also so this pattern 0 0 1 will push this pattern 0 0 1 will push a will make the output 0. So, if you are trying for so this particular pattern is sufficient to detect the fault which is E stuck at 1. So, under this 0 0 1, so this will be this E output is 0 in the fault free case. In the so if we are trying to check E stuck at 1, so this pattern is sufficient. So, once we have detected this pattern 0 0 1 for D stuck at 1 fault, we also can drop the fault E stuck at 0 from this set. Now, a fault may be untestable in which no test would be generated. So, if a fault is untestable due to some redundancy in the circuit, then that fault will not be detected by any test pattern. So, naturally that type of faults can be detected from can be dropped from the set. So, these untestable faults, if we can separate out from our test generation process, then the test generation process may be faster. Second case, an ATPG may abort on a fault if the resources needed exceed a preset limit. So, ATPG needs to run. So, it requires CPU time, it requires memory for its operation. So, if it is the case that for testing a particular fault, it is requiring very huge amount of time. Okay. So, it is the process is continuing, it is not over, but due to the circuit structure or due to the nature of fault, it is happening that it is taking large amount of time. So, after a certain limit, maybe we can drop that fault and we can say that okay, this fault will not be detected. So, this is this fault is not redundant or this fault is not untestable, it can be tested, but the current setup of ATPG is not able to do that. So, instead of just looking behind this particular fault, the ATPG will look for some other faults, because ultimate goal of ATPG is to improve fault coverage. So, if it can detect some other faults, the fault coverage can be improved. Random test generation. So, this is the simplest form of test generation. So, we generate n randomly we generate n random test patterns. So, this random test pattern, so basically it is a if it is a two valued logic. So, you apply random 0 1 patterns to the inputs and see whether what type of output it produces. So, we are generating a random pattern and then we are looking into the fault free response, then we try out all possible faults in the circuit one at a time. So, if it is stuck at one model that we are stuck at fault model that we are considering, so it will insert one stuck at fault and see whether that fault is getting detected by this particular pattern. So, it basically does a fault simulation. So, after fault simulation, it will know what are the faults that are detected by this particular random pattern and all those faults are dropped. Then it will go for the next pattern, generate another random pattern and see whether any of the remaining faults are covered. So, this way it does the random test generation. So, if we are trying to see what is the level of confidence on a random test set T, the probability that T can detect all stuck at faults in the given circuit. So, this is the measure of confidence, and quality of a random test set highly depends on the underlying circuit. So, some circuits they have got faults which are mostly getting covered by random patterns. So, they are easy to detect, and some faults are there in the circuit which are random resistant faults. So, they actually require a specific type of pattern to be applied to the circuit for detecting that fault. So, that way the possibility of detecting that fault in a random fashion is difficult. So, naturally they are called random resistant faults. So, to solve this random resistance problem, so what is done is sometimes we bias the inputs of a random resistant fault. So, how do we make it this weighted random pattern? Like, let us take an 8 input AND gate. Now, if we do not have any biasing, then all the 8 inputs of this AND gate has got probability of 0.5, at the input. So, if we are trying to check whether what is the probability of getting a logic 1 at the gate output, so that is 0.5 to power 8, it is 0.004. So, if we are trying to check a fault which is say AND gate output stuck at 0. So, for checking that 8 input AND gate output stuck at 0, so this line stuck at 0. So, I need to push a 1 at this point. Now, to push a 1 at this point, I must be able to apply all 1s at the input. Now, since they are all these inputs are generated through a random process in my random number in my random test pattern generation. So, probability of getting 1 here is 0.5, here it is 0.5. So, the probability of being able to produce a 1 at the output is 0.5 to the power 8. 0.5 to the power 8. So, that makes it cumbersome. So, the probability becomes very low, it is 0.004. Now, if we can bias the inputs, so that the probability of generating logic 1, probability of getting 1 at an input is 0.75 instead of 0.5. So, this random number generator is modified in such a fashion that in 75% cases it generates 1 and 25% cases it generates 0. So, in that case, the possibility of getting a logic 1 at the input in each of the input is 0.75. So, the overall probability of getting a logic 1 at the output of the AND gate is 0.75 to power 8. So, it is 0.1. So, you see that from the probability 0.004 it has increased to the probability has increased to 0.100. So, by changing this input probability, so we can force certain certain gates to go to a particular value, logic value. The chance of going to a particular logic value will increase. However, this obtaining an optimal set of input probabilities is a difficult task. So, that is the first thing. So, because that is the analysis that we have shown is for a very simple AND gate, but if it is a complex circuit and we want to do this for all the points in the circuit. So, that way getting optimal input probabilities will be difficult. So, what to do? We want to increase the signal probabilities of hard to test region. So, what is the hard to test region? So, if this is a the full circuit, maybe we generate first we apply some random pattern. So, these are the inputs to the circuit. So, we apply some random pattern. Suppose the faults that are present in these regions of the circuit, they are detected, but we see that a particular region of the circuit, so it is not responding to these random patterns. So, in that case, so we know that this region has got faults which are random resistant faults. So, for this, so then we find out the cone of influence for this particular region. Maybe this is the cone of influence for this particular region. So, what we do? We change the input probabilities for these inputs, so that we can get a more biased random pattern generation that can target faults in the hard to test region. So, this way these random pattern generators, so they can be modified, and accordingly we can get some better test pattern set which will be detecting more number of faults. So, probability of fault detection. So, given a circuit, suppose it has with n inputs, if Tf be the set of vectors that can detect fault f, then Df is Tf upon 2 power n, it is the probability that f can be detected by a random vector. So, if this f is detectable, then out of these 2 power n vectors, at least one vector will be able to detect it, and if this Tf can detect fault f, then this Df is the detection probability Df is defined as Tf by 2 power n, and naturally Ef is 1 minus Df is the probability that a random vector cannot detect f. So, this is important. So, if Ef is high for some fault, we know that the fault is going to be random pattern resistant fault. So, Ef power n is 1 minus Df power n is the probability that n random vectors do not detect f. So, if I apply instead of single random vector, so since random vectors they are all independent of each other. So, if we repeat this experiment n times, then it is Ef power n is 1 minus Df power n. Thus, the probability that at least one out of n random vectors can detect f is 1 minus df power n. So, this is the probability that at least one of the n random vectors will be able to detect f. What is the minimum detection probability? The minimum detection probability of any detectable fault actually does not depend on n, the number of primary input, rather it depends on the largest primary output cone that it is in. So, what it says is that, say this is the fault that we are going to detect. Now, if you see that this is the input cone that we have. So, it does not depend on n is the number of inputs, number of primary inputs of the circuit, rather it depends on this value, because this so suppose this output goes to it goes to several this point signal line point f, it goes to several outputs, say this one and this one. Out of that, for each of these outputs we have got an input cone of influence. So, input cone of influence of a primary output is the set of primary inputs on which that particular output depends. So, by doing an analysis or traversal from the primary output towards the primary input, we can identify this type of cones for individual outputs. Now, whichever cone is the largest, that has got the largest number of primary output. So, that way primary input. So, that way so it will depend on that, because in the worst case this fault will get detected and it will propagate to this output, and in that case it needs to be controlled by all these primary inputs. So, this is so this path excited, this fault excitation and fault propagation. So, this whole job can be done by setting this the inputs in this cone only. So, the inputs which are outside this cone does not have any effect on the excitation of this fault or propagation of this fault to the primary output. So, this is the thing that minimum detection probability. So, it will depend on the largest primary output cone into which this particular fault falls. So, there is a result that tells that in a combinational circuit with multiple output, let n max be the number of primary inputs that can lead to a primary output. So, if you consider all primary output cones, so n max is the maximum number of primary input associated with some associated with the primary output. So, there may be a number of primary outputs. So, for each of them we compute the cone, and we find that for the largest number of inputs associated with any primary output is n max. So, then the detection probability for the most difficult detectable fault is d mean greater or equal 0.5 to the power n max, because this will be the each of these inputs may be set to 0 or 1. So, as a result the probability is 0.5. So, 0.5 to, so each of these inputs are to be set to some value, and that way it is 0.5 to the power n max. So, d mean will be greater or equal this quantity. So, that gives a better estimation of the number of the detection probability of a fault. Next, we will look into different test generation techniques. To start with, we will look into exhaustive test generation. So, exhaustive testing, it says that apply 2 power n patterns to n input combinational circuit under test. So, what we mean is that this is the circuit, it has got n number of inputs, this has got n number of inputs. So, irrespective of what this what type of faults that may be present, etc. So, ultimately we are going to apply one of these patterns, like these n inputs can have at most 2 power n different combination, different permutations, different combinations that can come here. So, naturally I can so any test pattern is nothing but a combination from these 2 power n set. So, in the worst case, so if we apply all 2 power n test patterns, all 2 power n possibilities to the circuit, then we should be able to detect all possible detectable faults in the circuit. So, this is the exhaustive testing. So, we apply 2 power n patterns to an n input combinational circuit under test. It guarantees that all detectable faults in the combinational circuits are detected. because no more pattern we can apply. Any test pattern set is a subset of this 2 power n. Test time may be prohibitively long if the number of inputs is large. So, if n is small 10, 15, 20, so okay fine, so we can do this thing, but if n goes to hundreds, then it is out of question. So, it requires huge amount of time. So, it is feasible only for small circuits. So, this is the exhaustive testing, but the advantage is that we do not need to consider the type of faults that are present. So, for every fault that can be detected, so we have applied a test pattern to the circuit. So, all those faults will get detected. So, we do not need to consider the fault models. Another category of this exhaustive testing is a pseudo-exhaustive testing. So, in this case the partition the circuit into cones. Okay. So, one primary output depends on a subset of inputs. So, it is not necessary that to excite all possible outputs at all possible outputs for the primary output line. So, it is not necessary to excite all the inputs. So, it is only necessary to excite the input cone with all possible patterns. So, that way if we can partition into cones and we exhaustively test each cone. Okay. So, then that way the complexity may be less, but still guarantees to detect every detectable fault based on the previous result that we have shown, that the D mean expression. So, continue in the next class.